All right, in this video, we're going to talk about multiplying power series together. You got to be a little bit careful when doing this. It's not quite as straightforward as you might hope, but we're going to talk about a bit of a process for how we can develop the idea of multiplication. This product that we get from this multiplication, we call the Cauchy product of power series. We have our representation of two different power series here, which is very, very standard. Cn and d sub n just represent our coefficients of these power series. What we're looking to do is to multiply these two together, which are represented here by these expanded forms. And the beauty is, to multiply these, we're just going to use the properties of multiplying polynomials together. Now, these are infinite sums. I'm not going to take an infinite amount of time to do this. Even though I've expanded these up to the third degree term, I'm only going to go to the x squared term when doing this, just because the board space gets ridiculous if I try to go beyond that. So what I'm going to do is just starting with this first power series, I'm going to take this first term and multiply it through, next term, multiply it through. And again, I'm reserving the right to stop with my analysis once I get past an x squared term. So first of all, I'm going to multiply C0 by these terms here. So C0 times D0 is C0 D0. C0 times this term right here would just give me C0 D1 x to the 1. And then C0 times this term right here gives me C0 D2 x squared. And then that, I'm not going to do that cube term. Again, I digress. I'm going to move on now to this C1 x1. I'm going to multiply that by this first term. So what I get is C1 D0, and I have a factor of x now I'm starting with. Then next is the C2 or C1x times the D1x. So that's going to give me C1 D1 x squared, because those each have a power of x. If I multiply that now by this, I'll get x cubed. I'm stopping. And then I only have one more thing to do. So I have C2 x squared times the d sub 0. So I get that, d0, and that's x squared. If I multiply that even by this next term, I'm now going to have a cubed term, and I'm stopping. I'm feeling good about that. What I'm now going to do is to organize these, and we're going to see a pattern in these coefficients without explicitly reorganizing all of this and then factoring. I'm sure that you can see what I'm doing right here. I only have this one constant term right here, which is C0 D0. And then for my x's, I have these x's here and these x's here. So if I factor out an x from those, what I'm going to get is C0 D1 plus C1 D0, and that's the coefficient for x. And then for my x squareds right here, what I'm going to get is I get C0 D2 plus C1 D1, and then C2 D0. Hopefully you can see the interesting pattern that's going on. We're going to write a generalized statement for this. But one thing that I noticed right away is that if you look at the powers of the term you're looking at, and then these indices right here, these indices always add up to the power that they're representing. So 0, this is x to the 0 power. Adding these two together, you get 1, and it's x to the 1 power. And then each of these are the combinations of writing 2, 0 times 2, 1 plus 1, and 2 times 0. To get to that power of 2. And what naturally happens as you look at expanding this is that we have, for the C's, for the C power series, the coefficients for this first power series right here, they're progressing up by 1. And then the D's, which come from the coefficients of the second series, are starting at the highest and going down, given whatever power or degree of term that you're in. Right, to generalize this, we'll actually need to use two little summations. So one summation to describe these coefficients that we're looking at, and then an infinite sum to describe the whole power series. But what I'm going to do is use g sub n to denote the nth term's coefficient. And so again, just to see what's going on here, we have this summation. This is going to be a sum where the c sub n's start at 0 and then go up by 1. And then what happens with the d coefficient that's multiplied by it, it starts at the end, again, the end being whatever that exponent is right there, and then going down. how we can do that is write this summation. Let's use k in this case. We start at 0 and go to n. So the summation, again, to represent these right here would be c starts at k, and then what d does, it starts at n minus k. So what this means is when k is 0, this is going to start at the end, or in this case at 2. And then as we iterate k, this goes down and this goes up, keeping that same balance right there. But if we define those coefficients to be this right here, then this multiplication of these two series will equal the infinite summation from n equals 0 to infinity of the g sub n coefficients described right here times x to the n. And beautifully important to this is that now that we have this definition for the way to multiply these, if we then were given information about the convergent nature of these two power series, so the first power series with these c sub n's converges to f of x on an interval, and then on the same interval of convergence, this second series converges to g of x, then what we actually know from this product right here is that this product, defined like this, will converge to the multiplication of those, exactly what we were looking for. So f of x times g of x on that shared interval of convergence. Finally, to say, you won't actually have to memorize this formula and this whole setup right here. But what you'll have to know is that when you go to try to multiply these, you're going to have to expand out, at least with a few terms, it's expansions of these power series to get an idea of what these new coefficients look like. All right, so in this example, we're going to use that idea of multiplying power series together, get a feel for how we construct the power series, and just being careful when dealing with the coefficients in our final example right there. But it's no surprise, we're using our best friend power series here for 1 over 1 minus x, and we're looking to construct a power series for 1 over 1 minus x squared. What I'm going to do right away is think of this as instead of 1 minus x times 1 minus x, or in other words, think about this expression like this right here. And again, if you were watching those previous examples with my other rational function that I used partial fractions with, one, it wasn't as easy to maybe write those out, but then also I didn't have to think about multiplication. With partial fractions, I thought of that as addition. Here, I'm just going for it. I'm going to think about this as the multiplication of these two functions right here. And then each of these can be represented by that simple power series right there. So what I'm going to be thinking about is the multiplication of this just basic power series right here. And to really think about this, I need to think about these expansions of these. So each of these are 1, then plus x squared, and plus x cubed. Again, I'm not going to go too far with each of this, or this multiplication at all. Though this time when I multiply, I'm going to go all the way up to x cubed because I really want some real rigor here. Nah, not really. It's just easy, and I'm going to show that. So when I multiply first 1 into all of these, so I get 1 times these. It's just a copy of each of these. So plus x squared plus x cubed. And then the only difference is now when I multiply it by the x, the first one just gives me an x right here, and then an x squared, and then an x cubed. And then an x to the 4th, but I'm not going to write that. Move into the x squared, I get plus x squared, and then plus x cubed, and then x cubed, I get x cubed, and then right away, I'm too far, I have an x to the 4th. So the question is how to think about generalizing this and what's going on? Well, let's look at these first 3 powers, first 4 terms. I have my constant of 1 right here, and then I have 2 x's, so that'd be 2x. And for my x squareds, I have 3 x squareds. I think I know what's going on right here. This coefficient is 1 more than that exponent, but let's just double check with these x's. 1, 2, 3, 4, 4 of the x cubes. Feeling very confident then what I see is going on. And that makes a lot of sense given the nature of this multiplication. I'm just adding a power each time. So if I wanted to generalize this, so this multiplication of these two, what I would get is the summation from n equals 0 to infinity of n plus 1 times x to the n. So what do I know? Well, the previous statements we had was that we know that the power series created by the multiplication, this Cauchy product of these two power series, which is this right here, this is a power series that represents the multiplications of whatever these represented over a given interval. They have a shared interval because they're the same. So what that means is that this representation right here, so this from n equals 0 to infinity of n plus 1 times x to the n, this right here represents 1 over 1 minus x squared on an interval of convergence for x from x's absolute value of x is less than 1, or as I was thinking about it in my head, you could also just say this from 1 or negative 1 to 1, same statement. The important thing to take out when you're multiplying series is that you're not then just going to multiply the terms of those series together. It takes some work. We had that generalized form that we were just talking about, but almost always how you'll go about doing this is do a small expansion of these series and get a feel for the coefficients and the terms of the series to create a representation. But if you're able to create a representation of that multiplication of those power series, then you're confident to know that that representation here represents those two functions that are represented by the power series being multiplied together, as long as they have a shared interval of convergence.